Okay, we're going to start a very quick revision of complex numbers up to this point. So the whole idea of complex numbers is to be able to solve things like square root of minus 4. So I define the imaginary number as a number that when I square it, I get minus 1. So square root of minus 1. And I kind of write complex numbers like this, where I have a real part and I have an imaginary part. Square root of minus 4, incidentally, would be 2y. Square root of 4 times square root of minus 1, so it would be 2y. So I have a real part and an imaginary part. A complex number has a real part and an imaginary part. The imaginary part is multiplying the imaginary number I. And this form here is going to be the Cartesian form. So I can represent it in Cartesian axis, where instead of having an x and y axis, I have a real axis and I have an imaginary axis. And I can represent it, this will be 2 plus I, because the real part is 2 and the imaginary part is 1, and so forth. The other way to represent it is using this thing called the polar form, where I use the modulus, which is how much would I have to walk to get to this blue point from 0, 0, and the angle, which is a way to reference in which direction I have to walk in to get to this point here. So I get to the same point, hence I'm representing the same complex numbers using the modulus, using the length, using the angle. To calculate the modulus and the angle, that is to change a complex number from Cartesian form to polar form, I would use Pythagoras and I would use the tangent. And hence I can write it in polar form. And if I have to change it to Cartesian form, I would use the sine and I would use the cosine, and hence I can write it in Cartesian form. Okay, it's a bit more than a minute, but I just want to make sure we make this quick revision before we move on. So what's the next thing that we're going to do? We're going to keep in mind that since I'm changing to Cartesian form and I'm using the sine and the cosine, this is what I end up with, right? I end up with the modulus times cos of theta plus I sine theta, right? Now, I take the modulus out and I make the common factor, and hence I end up with this expression. Well, it's going to be such a common expression that I'm going to actually have a shorter way of writing this, which is going to be the following way, where R is the modulus and CIS is just short for cosine plus I sine, so CIS. And I just put the angle. Since the angle, the argument is going to be the same here and here, I just put it once. And it's just a short way to write it. So whenever I'm writing something in the polar form, I don't write the modulus is equal to this and the argument is equal to this. I just write whatever the modulus is times CIS and the argument, and that's it. That's quicker, that's easier. So CIS is just a short way of writing this, and R is just, there you go. So, okay. I want to talk about complex conjugates. This is really what this video is about. So if we talk about complex conjugates, what's the whole point of it? Let's take first a look at a situation in which you will have encountered imaginary numbers without even knowing it. Let's solve this quadratic equation. You solve it, and many of you will be familiar with the following expression. You do minus b plus or minus square root, blah, 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 and you end up with a negative number here. Now, back in the day, you would stop and say, okay, no more, there's a mistake here, dear. Not anymore. Now you can keep on going, because you know the square root of minus 4 is going to be 2i, and hence I can simplify and end up with the following solutions. I end up with two solutions, minus 1 plus I and minus 1 minus I. That's simply the two solutions of this quadratic equation. Okay, so look at these solutions for a second. What I have here, and I think there's a typo here, I should say minus 1 plus I, minus 1 minus I, never mind. I have these two solutions. The only difference they have between them is the sign of the imaginary part. That's the difference they have. And actually, this is what we're going to be studying. This thing that naturally occurs when we try to solve a quadratic, that I have two solutions and the only difference between them is the sign of the imaginary part, is something that's going to happen a lot. And the relationship between these two numbers that are so similar, only difference being the sign of the imaginary part, is what we're going to study here, because we say that this number here is the complex conjugate of this number here and vice versa. So the notation for a complex number z, the complex conjugate is z with a little asterisk on top, with a little star on top of it. And the only thing that changes in z with a star on it is that the sign of the imaginary part changes. So if I have this complex number here, the complex conjugate is this one here. If I have this one here, the complex conjugate is going to be this one here, and so forth. Great. Now, if you try to do the following operation, some interesting things are going to happen with complex conjugates. They have what you would say a few properties. Like, it's not only that the fact that they appear a lot when solving equations, it's also that they have some properties between them. Try to do the following things. Try to add two complex conjugates together. If I add 2 plus 3i plus 2 minus 3i, well, the imaginary parts are going to cancel each other out, right? Plus 3i minus 3i, they go away, end up with 4. If I multiply them together, something very interesting is going to happen too. And actually, when you multiply them together, also you're going to end up with no imaginary part. I recommend you do that. So there are a lot of properties associated with complex conjugates, so they become a useful tool for us to use when we're calculating things with complex numbers. Let me give you an example. Okay, before the example, excuse me, here's a representation of a complex number and its complex conjugate. In polar form, you could say another property, in polar form, the only thing that's going to happen is that the argument is going to change sign. So if it was 30 degrees here, now it's going to be minus 30 degrees here. That's what happens with the complex conjugates if you look at it from the polar form. More useful properties. And these ones, you can prove them yourself if you want. It's not that hard, but I don't think they're really that necessary, but it's good for you to have them in hand. If I add two complex numbers or subtract two complex numbers and then make the complex conjugate of the result, it's the same thing that if we make the complex conjugate of each one of them and then add or subtract it together. Same thing if we're multiplying, dividing, or if we're making powers. Those are my extra properties I really want to mention. Honest with you, I don't think they're that necessary, but you never know, so keep them in mind. At least keep in mind that there are some complex conjugates properties out there that might turn out to be useful. So what do I use this complex conjugate thing for? This is what you do with it. So suppose you have the following expression, okay? I have to divide this thing. This is a complex number divided by another one in Cartesian form. That would be great if it was in polar form. I just have to divide the modulus and subtract the arguments, but I don't have that. So here's another trick to do it. Use a complex conjugates. Because if you multiply this thing, this expression here, times the complex conjugate of the denominator, and you can't do that because realize that this and this is the same thing, hence I'm just multiplying by 1. I'm going to be getting the same thing, so I'm multiplying by 1 ultimately. What's going to happen is the denominator is going to be, again, a complex number multiplied by its complex conjugate. And as we saw before, I'm going to get a real number. The imaginary part is going to disappear. So I'm going to end up with this, which again is 13 plus 39 divided by 26. And I can simplify this actually, and I end up with something that's much more nicer complex number with a clear real part and a clear imaginary part. So summarizing, this would be the result of this division in Cartesian form. And rather than switching to polar form, I can do it just using the complex conjugate. It's just a nice little trick.